Hi, welcome to the first lecture of Chem 1010, General Chemistry. Today we're going to be talking about quantum theory, and that might seem sort of a strange place to start in a general chemistry class, but the subsequent chapters we're going to be going through all build off of this information, so it's a very important place for us to start. And you can see by the title, which was a quote by Werner Heisenberg, this is all very strange stuff. So if it seems weird to you, don't feel bad, because it seemed weird to the people that were making these discoveries. And the picture is a play on Schrodinger's cat, which is a famous thought experiment. And in the end of the lecture today, I'm going to go into the details of that thought experiment a little bit and show you just how crazy the implications of quantum theory are. Now, this is probably closer to physics than it really is chemistry. So if you're strong in math, strong in physics, I think you'll actually like this part of the class, this section. You're going to do well. If you're not so strong at math, don't worry, because the math we're going to be doing in this class is all very simple. There's no calculus involved, so you should be able to succeed. So why should we care about quantum theory? Why study it? Well, it turns out at the turn of the previous century, in the 1900s, there are many observations, many discoveries taking place that were conflicting with the classical view of the universe, in particular with the properties of light, matter, and energy. And why we care about that as a chemist is that the interaction of matter and light is very important. This is how we study molecules and chemicals, is by spectroscopy. In this class, why it's important is that quantum theory is used to explain chemical periodicity, which we'll be talking about in Chapter 8, chemical reactivity, also in Chapter 8, and molecular shape, which we'll be talking about in Chapter 10. So there were three questions, three observations that classical theory really was not very good at answering. The first was black body radiation, also known as the ultraviolet catastrophe. Second was the photoelectric effect, and the third were spectral lines. And we're going to be talking about all of these in some detail later in the lecture. I want to point out now this green triangle here on the slide. Anytime this quarter that I'm present something that I don't really feel like you need to know for an exam, I'm going to have this green FYI rectangle on the slide. And that's just to let you know that you don't have to memorize this. This is really just for your information, for your interest. And this is a chart that was in your book that details the types of discoveries that were occurring around the turn of the century. And in our case, quantum theory was really started in 1900 by Planck. And it finished with the development of Schrodinger and Heisenberg, the development of quantum mechanics, and that was the late 1920s, early 1930s. So it was this 20 to 30 year period of development at the beginning of the 1900s that was really important for quantum theory and changing the way that physicists, scientists look at the universe. And if you you look on this list, there's also some other interesting discoveries that took place. 1897, the discovery of the electron. We talked about that a little last time. Rutherford's nuclear model, 1911. Something that isn't on here was 1932. That was the discovery of the neutron. So the electron was 1897. Proton was around 1910, 1911. And it was another 20 years till the neutron was discovered. And that might not be surprising because it's neutral. The electron and the proton were charged. They're much easier to find than the nuclear subatomic particle, the neutron. And this is a list of key concepts to understand. Now this, I don't expect you to go through this all right now. I just wanted to point out that this is in the back of your chapter, in chapter 7. There's a list of skills and a list of concepts. So it's important that after you finish reading it, a chapter, that you look at these concepts and make sure you understand, make sure you're getting what you're supposed to be getting out of the chapters. And I broke the skills down a little bit. We'll go through those a little bit in more detail. I won't be going through any of the subsequent chapters, any of the key skills, but I wanted to go through this one just to give you a heads up. The first skill was be able to convert between frequency and wavelength. We're going to go through how to do that. Calculate the energy of a photon. That's using Planck's equation. Find the energy of a line in the spectrum of hydrogen atom. That's Bohr's model. I want you to be comfortable using the work function and apply it to problems with the photoelectric effect. You should also be able to use de Broglie's equation to find wavelength of a particle. And then you should be able to apply the uncertainty principle to find uncertainty in speed or position of a particle. And finally, probably the most important skill to have when it comes to taking chemistry classes further down the road, be able to determine quantum numbers. So that's probably the most important skill in future classes. Be comfortable with quantum numbers, determining them. So if we start in Chapter 7, Section 7.1, we're going to talk about the nature of light. So the different properties of light, the behavior of light. What is light? Well, light is also known as electromagnetic radiation. So I'll be using those terms interchangeably. And why is it called electromagnetic radiation? That's because light consists of an electric field with a magnetic field that's perpendicular to it. And this was postulated by Maxwell around 1860, and it was confirmed about 25 years later by Hertz. So really needed to understand the properties of light before the discoveries in quantum theory could take place. Here's a picture of the electromagnetic spectrum. We have, you can see that it's a very broad spectrum. We go from, here's frequency. It goes from 10 to the 24th hertz to 10 to the 4th hertz or so. That's 20 orders of magnitude. Something important to notice here is that the higher the frequency, 10 to the 24th, the smaller the wavelength. And the lower the frequency, the higher the wavelength. So they're inversely related. We're going to talk about that a little bit more in a minute. You'll see at the high energy side we have gamma rays, X-rays, ultraviolet. And between ultraviolet and infrared we have this small sliver, and that's the visible spectrum. And us as humans, naturally, we interact with our environment through the visible region. of the spectrum, and it's only a very, very small region. There's much more frequencies, wavelengths of electromagnetic radiation out there, but we can only see a very small amount. Some of the longer wavelength, lower energy regions of the spectrum are microwave and radio. And all of these spectrum, all these regions in the spectrum are utilized by scientists to study the universe. And in chemists, for instance, we use X-rays in crystallography. We use ultraviolet and visible light to determine electronic structure of molecules. We use infrared light to determine the bonding, the nature of the bonding in a molecule. We use microwave radiation in a technique called electron paramagnetic resonance, where we're studying unpaired electrons in molecules. And we use radio radiation, the radio band of the electromagnetic spectrum, in a technique called NMR, nuclear magnetic resonance. So all of these the whole range of the electromagnetic spectrum is utilized. What are some properties of light? The first property we're going to talk about is wavelength, and that is denoted by the Greek letter lambda. And the wavelength is the distance from the crest to the crest of a wave, or the trough to trough. So here we see wave A, the distance from crest to crest on this particular wave is 1, 2, 3, 4. 4 units. The next property that light has is a frequency, and that's denoted by Greek letter nu. It looks like a V. It's actually the Greek letter nu. Some texts use a lowercase f for frequency, but we're going to use the nu. And frequency is the number of times a wave passes a point per unit time. Now if we look at a different wave here, wave B, we see that the wavelength of wave B is 1, 2 units. So wavelength A is 4 units, the wavelength of B is 2, so wave B has a wavelength that is twice as small as wave A. Now if we let's just imagine us sitting on this point on the axis, how many times does that wave pass? For wave A, it's once. For wave B, it'd be 1, 2 times. So we can say that the frequency of wave B is twice as much as the frequency of wave A. The last property that we're going to discuss is the amplitude, and this is the height of the wave. If we look at two different waves here, wave C and wave D, they both have the same wavelength, but you notice that wave C has a higher crest. So we say that its amplitude is higher than wave D. Now, frequency and wavelength are related by this expression. Wavelength times frequency equals C, and C stands for the speed of light. In particular, it's the speed of light in a vacuum, but in this class, we're going to always assume that when you use C, it's speed of light in a vacuum. We're not going to take into account different media that the light is in. We're always going to assume that light's in a vacuum. It's also important to remember when you're using this equation, wavelength has to be in meters and frequency has to be in hertz or inverse seconds. And also, the book gives this value for the speed of light. Don't remember that. Just remember 3 times 10 to the 8th meters per second for speed of light. And on an exam, you're going to be given all the equations you need, and all the constants. So you're going to be given this on exam, so you don't have to memorize this information. What are some important behaviors of waves? Well, the first is refraction. What is refraction? It's when light bends when it passes between two different media. So the classic example is when it's going from air to water. You get a bending of the light. Another important behavior is diffraction, and that is when the light passes around the edge of something or through a narrow opening, you get a bending of the light. And finally, interference is when light waves interact, and you can either get addition or reinforcement of those waves, and that leads to constructive interference, or you can get subtraction, canceling out, or what's known as destructive interference. Here's a picture that depicts what refraction is. You have a beam of light going into a prism. In that prism, it bends, the light bends, but it bends differently depending on the wavelength. So red has a longer wavelength, it bends less. Light with shorter wavelength, like the blue and the violet, bend more. So what that does is actually spreads the beam of white light out into its component colors. And this refraction will be important when we talk about atomic spectroscopy here in a few minutes. The other properties, diffraction and interference, if we look at those more closely, let's envision that we have light heading towards an object here that happens to have two slits in it. Now, if you think of this as a pool of water for a second, and this barrier is something like a dam, but it has a couple holes in the surface. Now, when those waves of water hit that dam, some water is going to come through those two slits, and it's going to make waves that propagate out in a circular fashion. Now, when these waves interact with each other on the other side, you're going to get some waves that are in phase, some waves that are out of phase. The waves that are in phase, where the crests and the valleys match up, you're going to get an addition. So that'll be a constructive interference. Now, if we put a screen up on the other side to actually visualize the light, at those points when there's constructive interference, there'll be light lines. Conversely, at some points, the waves aren't going to match up. You're going to have a crest match up with a valley, and they're actually going to subtract one another, destructive interference, and you get dark lines. And so this pattern of light and dark is what's known as a diffraction pattern. And we're going to see an example of this later in the lecture that led to the discovery that particles can have wave properties. Well, speaking of problems, the first real problem that classical theory couldn't answer was what's known as the ultraviolet catastrophe, or also known as black body radiation. So in general, black body classical theory predicted that an ideal black body would emit radiation with infinite power. So that's what's depicted here in this plot. Classical theory here shown in this black line. And that's not what was seen. Observation was shown here at different temperature in these colors. And I don't expect you to remember this plot. In this class, we're not going to really go into the details too much about this. but all we want to really know is that this was really the driving force for the start of quantum theory. So observations did not match the theory. And that's where Max Planck came in. He sort of as a last resort decided to invoke energy was only allowed to have a certain discrete packets, and that actually this crazy idea he had to try to solve this problem worked, and it was the foundation of quantum theory, and he ended up winning the Nobel Prize in 1918 for this. So let's talk a little bit about particles versus waves. So some light property was not really explained by wave theory, in that the black body radiation, the ultraviolet catastrophe, was one of these properties not very well explained. So he proposed that light had some particle-like properties, and that radiant energy had particle-like properties to it that he called quanta. And quantum theory is really based on this idea that energy is absorbed or emitted in discrete quanta. It's not a continuum. There's actually discrete steps. And that's where we get the name quantum theory. Quantized means having discrete values, restricted to whole number multiples of a scientific base value. And Planck called these quantum. Einstein, a more common name for these, are photon, and that was coined by Einstein. And the energy of a quantum of radiation is given by what's known as Planck's equation, and this is, again, an equation we're going to use quite often, and that is the energy is equal to h, which is Planck's constant, times frequency. In another way you can write that, if you remember the relationship between frequency and wavelength, energy equals Planck's constant times speed of light divided by wavelength. So it might be helpful to remember both of these equations, or be able to convert from one to the other. A graphical representation of what a quantized state is shown here. A quantized state is like a staircase. You can go from one step to another, but you can't be in between steps. And contrast that to what a continuum state would be, in that's more like a ramp, where you can be any height off the ground you want to on that ramp. But a staircase, there's only discrete steps that you can take. So let's try a practice question. Right. A mole of blue photons with a wavelength of 470 nanometers is sufficient to drive which of the reactions below? And I have written down a couple relationships that you find useful, and a couple constants, Planck's constant and the speed of light. So you should be able to solve the energy of the blue photons and find which of these reactions that could be driven by blue light. And also, if you remember Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. All right, take a few minutes, answer the question, and then continue on, and we'll work through the answer. Okay, so the first step we want to do when answering this question is to calculate the energy for one blue photon. So for that we use Planck's equation. E equals Planck's constant times frequency. But then we can use the relationship between frequency and wavelength because we're given wavelength in the problem. Substitute that in for the frequency, and what we get is Planck's constant times the speed of light divided by wavelength. Now we can plug those values in. We get E equals 6.626 times 10 to the minus 34th joules seconds. Remember to always keep your units so you see if you're doing everything correctly. C is speed of light, 3 times 10 to the 8th meters per second. And wavelength is 470 nanometers, but the units for speed of light are in meters, so we want the wavelength in meters. 470 nanometers one nanometer is 1 times 10 to the minus 9th meters. You can also do it the other way. One meter is 1 times 10 to the 9th nanometers. So you're dividing by 10 to the 9th, or you're multiplying by 10 to the minus 9th. So we can write 470 times 10 to the minus 9th meters. Then we'll get meters to cancel, seconds will cancel, and we'll be left with a value of energy that's in joules. And what we should get when we do this is 4.23 times 10 to the minus 19th joules. So that is the energy of one photon of blue light. So we can write that as joule per photon. And it's important to remember that when you use this equation, Planck's equation, you're calculating the energy of one photon. So now we have to find the energy of a mole of these photons. And that's where we use Avogadro's number, which is 6.02 or 6.022 times 10 to the 23rd things per mole. And in our case, the thing we're looking at is photons. So then we multiply our energy, 4.23 times 10 to the negative 19th joules per photon, times Avogadro's number, 6.022 times 10 to the 23 photons per mole, and what we get out is 254,730 joules per mole. Now, this answer's in joules, but our choices we're given are all in kilojoules. So let's remind ourselves it was 254,730 joules per mole. We want to convert that into kilojoules. So we write 1 kilojoule is equal to 1,000 joules. And that becomes basically 254 kilojoules per mole. So which one of these reactions could a mole of blue photons drive? Both B and C have higher energies than the 254, the number we calculated. So a mole of blue photons is not going to be able to drive those reactions. The correct answer would be A, because it has an energy of 241. So if you answered A, that's the correct answer. So a question like this, where these equations are fairly simple to use, you can still have sort of a little bit more tricky question coinciding with that, with using simple equations. The second observation that classical theory really wasn't able to answer, really wasn't able to explain, was the photoelectric effect. Now, what is the photoelectric effect? Well, people noticed that when they shined a certain wavelength of light on a metal, here we have a nice violet color of light shining on the metal, we get electrons kicked out of that metal to a positive electrode, and then it completes a circuit, and you notice that there's a needle here measuring a current. So you have a movement of electrons caused by this purple light. Now, when they took the same metal, the same setup, and shined a less energetic form, a longer wavelength light, shown here as red light, there was no current. And classical theory we're not really going to go into why it didn't explain it, but it didn't really explain this. And one of the reasons was because you can take a very weak, a very low intensity purple light and get a current, but you could take the brightest red light that you can come up with, the most intense red light, and you wouldn't get a current. So it really had nothing to do with the intensity of the light, the power of the light. It was all about the frequency or the wavelength of the light. So how does quantum theory explain this? Well, if you remember, we have Planck came up with his quanta, or Einstein liked to call photons, which have a discrete packet of energy. So Einstein postulated that the frequency of the light that you shine on the metal mattered because you had to have light that had photons of a certain amount of energy to be able to dislodge an electron. And that's where this work function comes in. It's the minimum energy required to release an electron from a metal surface. And it's given as the Greek letter phi, which is this circle with a vertical line drawn through it. And that is equal to Planck's constant times nu naught. And okay, again, phi is what's known as the work function. Nu naught is a threshold frequency. So above that frequency, above that threshold frequency, you're going to get an electron kicked off of a metal. Below it, you're not going to get, you're not going to be able to knock an electron off of the metal. And you can express the kinetic energy of the electrons kicked out using this equation. the kinetic energy is equal to h nu, the energy of the light you're shining on a metal, minus phi, the work function. And kinetic energy is a measure, if you're not familiar with that, it's a measure of the speed of an electron. So let's try a second practice problem using these work functions. So if we have a sodium metal and silver metal, they both have work functions. Sodium is 2.46 electron volts and silver is 4.73 electron volts. Now, if the surfaces of both metals are hit with the same light, which metal will give off electrons with greater kinetic energy? So take a few moments and think about this, and then we'll go through the answer together. For this question, you don't need to plug any real numbers in. We don't need to solve for kinetic energy. All we need to do is compare the two work functions. So the work function of sodium is 2.46 electron volts. Work function for silver is 4.73 electron volts. Now you can see that silver is larger. So if we have the energy of the light that's being shined on both metals stays the same. If we have a larger work function for silver, that means this energy has to subtract a larger value for work function, then the kinetic energy is going to be smaller for silver. So the work function for silver is larger. Therefore, the kinetic energy of that electron coming off of the silver will be lower. Now, if you wanted to, you could plug in any value for frequency you wanted and work through the math. But for a question like this, you don't really need to solve the math. You just need to look at the actual equation and the values for the work functions. So a larger work function means it's harder to kick that electron out. You need a frequency that's higher. The minimum frequency is higher. And it turns out that working on the photoelectric effect really pays off, or it did for Einstein. In 1905, he made a description of the photoelectric effect, and he won the Nobel Prize in 1921 for this. And this was after his theory was confirmed in 1914 by Millikan. And Millikan himself won the Nobel Prize in 1923 for his work on the charge of an electron, which we talked about in the first lecture a little bit. It's in chapter 2 if you're interested. So we talked about the nature of light and the first couple of real questions that classical theory couldn't answer, that quantum theory needed to be used for. In section 7.2, we're going to move on to atomic spectra. And this was the third observation that classical theory really was having a tough time explaining. Light can be used to identify elements. So if we have a flame and we're burning sodium metal in that flame, if we focus that light, put it through a prism so it refracts, that refraction spreads the light out, we notice we get two lines at distinct wavelengths. And this is the same for all elements. And each element will give it a different pattern of lines. So we can use this light from the elements to really identify an element in an unknown sample. Here's some other examples of these. There's hydrogen, helium, neon. They all have their own characteristic spectrum, pattern of lines. And an interesting side note on this is these spectra were actually used by Hubble to find evidence for expanding universe. So what he was doing is he's looking at galaxies, distant galaxies, and trying to record their spectra. But what he saw was the lines he expected to see were all shifted to higher wavelengths. It's known as red shifting. It's part of the Doppler effect. And what was causing that is the galaxies were all, what that means is they were all moving away. So as they're going further away, the light coming out from them is being, the wavelength of that light is being stretched out, which makes it come at higher and higher wavelengths than you're expecting. And he noticed that the further the galaxy was away, the more redshift there was. We've saw a couple examples of emission spectra. You can also have absorption spectra, known as absorption or dark line spectra. And this occurs when you have an exterior source of light and you shine that light through a sample. And then again, you focus the light, refract it through a prism to spread it out into a spectrum. And you notice the absorption is a little bit different. You have dark lines superimposed onto a continuum, like a rainbow of colors, and you have dark lines in these. And this absorption spectra is really more useful in the real world. Most of the instruments used today by people in labs are absorption instruments. So just to reiterate, there's two types of spectra. You have emission spectra, and those are bright line, and absorption spectra, which are dark lines. So here's an example, and you'll notice that these are the same element, and the bright lines of the emission spectra line up with the dark lines of the absorption spectra. So in the late 1800s, before quantum theory was proposed, scientists saw these spectra, these atomic spectra, and they really didn't know how to explain it. But one man, Johann Balmer, he was able to fit the frequencies for the four brightest lines in the visible series of a hydrogen spectrum. And he used this equation, which you don't need to remember this equation. But this is kind of his way of fitting the visible lines in the spectrum. And n has to be greater than 2 in this equation. Again, we're not gonna be using this equation. I bring it up though to point out the one equation we are going to be using is the Rydberg equation. And what Rydberg did was he used Balmer's equation and he just converted it instead of frequency to be in terms of 1 over wavelength, which is known as the wave number. And so here's what the Rydberg equation looks like. 1 over wavelength is equal to this constant r, which is the Rydberg constant, given by this long number. And then you have a quantity 1 over n sub 1 squared minus 1 over n sub 2 squared. And for the visible series, n sub 1 equals 2, and n sub 2 equals 3, 4, 5, and so on. So n sub 2 has to be greater than n sub 1 in the Rydberg equation. So let's try a third practice question. What is the wavelength of the line in the visible spectrum corresponding to n sub 1 equals 2 and n sub 2 equals 4? And which line in the emission spectrum above does this transition correspond to? So take a few minutes, and then we'll go through this together. Okay, so we're looking for the wavelength where n sub 1 is 2 and n sub 4 equals 4. So really, it's just a matter of simply entering in all these values. 1.096776 times 10 to the 7th, 1 over meters, times the quantity 1 over 2 squared minus 1 over 4 squared. So what I get for this, 1 over 2 squared minus 1 over 4 squared is 0.1875. When you multiply that by the Rydberg constant, I get 205.6455 units, or 1 over meters. Where the question's asking for the wavelength, so we're going to have to invert that. So if we take the inverse of that, what we get is 4.86 times 10 to the minus 7th meters. Now it's most of the time meters are expressed wavelength is expressed in nanometers. So if we convert that, what we would get is 486 nanometers. Which line does that correspond to? That corresponds to this line here, known as H beta, at 486 nanometers. So the Rydberg model showed that you could make a mathematic expression for these lines in the hydrogen spectrum, but it really didn't give any reason why. And that's where Bohr came in. So he theorized, he took the Rydberg equation and he combined that with Planck and Einstein's idea of quantized energy states. So what his model of the hydrogen atom said was electrons in the hydrogen atom can occupy only discrete energy levels, and they only exist in these available energy levels. And they may move between the energy levels, and they do that by either absorbing or emitting energy. And these energy levels are designated by a specific value of n known as the principal quantum number. And he wrote this equation, sort of expanding on the Rydberg equation. And this time, instead of in terms of wave number, it's in terms of energy. So the energy of a transition in the hydrogen atom is equal to minus 2.178 times 10 to the negative 18 joules times 1 over n squared final minus 1 over n squared initial. So what is an electronic state? An electronic state, it's an energy level that's allowed, that the electron is allowed to occupy. And some terms that are important to note when we're talking about these energy levels, these electronic states, one is the ground state, and that's the lowest energy level available to an electron. And the next term that you'll want to know is an excited state. What does that mean? It's any energy state that's above the ground state. Here's some graphical depictions of what the Bohr model was stating. I like the graph on the left. The plot on the right shows it in more spherical terms, if you want to think about it that way. So here we have the principal quantum number, the energy level, n equals 1, the ground state. And then we have higher energy states above that, n equals 2, n equals 3, n equals 4. And the lines of the spectrum of the hydrogen atom can be explained by these transitions. So if an electron was in n equals 2 state and it dropped to n equals 1, it's going to give off a photon of light with the energy level that corresponds to the difference between the state n equals 2 and n equals 1. And you'll notice that the states that drop down to the ground state are known as the Lyman series. Those are ultraviolet wavelengths that they give off. There's the Balmer series, the visible series, and those are transitions to the n equals 2 state. And then there's an infrared series, and those are transitions to the n equals 3 state. So if an electron goes from a higher energy level to a lower, it gives off light. It can also absorb energy from a lower state and move to a higher one, and that's again absorbing that energy to move the electron into an excited state. Some people might like this picture on the right because it shows the nucleus in the center, and then these electron states, allowed states, as sort of orbits around that nucleus. So the strengths of the Bohr model were that it actually really was very good at predicting the energy needed to remove an electron from an atom, which is known as ionization. And it allowed scientists to begin using quantum theory to explain matter at an atomic level. And it perfectly accounted for the spectrum of the hydrogen atom. So the limitations of it are that it applies to only one electron atoms. And we'll talk about ions a little bit more next time. So the atom or ion can only have one electron. Anything else, anything more complicated, it cannot explain. It cannot be used for. And the movement of the electrons in an atom is really less clearly defined than Bohr allowed. But really the biggest limitation that you'll need to know for this class about the Bohr model is that it applies to only one electron atoms or ions. Let's try a practice with the Bohr model. So using the diagram on the left and the Bohr model, what is the frequency of one photon of the highest energy line in the Lyman series? So the ultraviolet series, the highest energy line in the diagram, what is the frequency? Okay. So the first thing we need to do is calculate that transition. So the highest energy line is going to correspond to the biggest line. And that in this diagram is from n equals 6 to n equals 1. So the arrow is moving from 6 to 1. So n initial will be 6 and n final will be 1. So if we plug those values into the Bohr's model, the number I get out, hopefully it's correct, negative 2.12 times 10 to the 18th joules. So that's the energy of that transition. And the negative value means you're giving off energy. You're going from a higher energy, an excited state, to the ground state. If you switch the numbers around, so you're going from a lower energy to a higher energy state, is absorbing energy.
So if we're looking at the energy of a photon that would be given off, there's no such thing as a negative energy. So the energy of the atom has to equal minus E of a photon, and that's conservation of energy. We'll be talking about that later in the quarter. But for now, you can just remember that a photon, you're not going to ever have a negative energy. So if you want to, you would just remove that minus sign if you're asked to find the energy of the light that's given off from this transition. So that'd be 2.12 times 10 to the 18th joules for that photon given off. Now if we use Planck's equation, because the question is asking for the frequency, Planck's equation is the energy of a photon, energy of a photon is equal to Planck's constant times frequency. We can rearrange that equation to solve for frequency. So the frequency equals energy divided by Planck's constant, 2.12 times 10 to the 18th joules divided by 6.626 times 10 to the minus 34 joules seconds. The value we get is 3.2 times 10 to the 15th. Inverse seconds, or you can also write that as hertz. Moving on to section 7.3, and this is discussing the wave-particle duality of matter and energy. So if we take a moment to just summarize what we've looked at so far, we had the classical theory where matter was particulate and massive, energy was continuous and wave-like. We had three observations that really didn't
match up with classical theory. The first was black body radiation, and Planck came up with a new theory that energy is quantized to explain this observation. Second was the photoelectric effect. Einstein again used Planck's idea of quantized energy, and he postulated that light had particulate behavior, and it was quantized energy values. And the third was from atomic spectra, and Bohr used observations of these spectra, combined that with quantum theory, and that energy levels in atoms are actually quantized, and photons emitted or absorbed when electrons change these orbits. So after these findings, after these theories were able to explain observations, a scientist by the name of de Broglie came up with a theory to go the other way. And his thought is that if electromagnetic radiation behaves as a particle and a wave, could a particle, such as an electron, also behave as a wave? And de Broglie came up with an equation to describe the wavelength of a particle, given by this, where lambda is a de Broglie wavelength, m is the mass of an electron or any particle, u is the velocity, and h again is Planck's constant. And for this work, I should mention too that de Broglie won the Nobel Prize in 1929. So where did de Broglie get this idea? Well, the first was energy is quantized, Planck's equation. The second was something we really didn't touch on, but it's also probably what Einstein was most famous for, is his equation E equals mc squared. So what de Broglie did was he took both of these equations, they're both in terms of energy, and he just set them equal to each other and rearranged them. And what he got out was his equation that gives the wavelength of anything. So all matter exhibits properties of both particles and waves. Electrons have wave-like motion and therefore have only certain allowable frequencies and energies. And this is what de Broglie was using to explain why quantum theory was working in terms of Bohr's model. So if we look at electrons as waves, electrons in an atom behave as a circular wave oscillating around the nucleus. Regions of standing waves have zero displacement and are called nodes. So if we think of that as a string on an instrument, like a guitar or a violin, you can have a standing wave. If you just pluck the string, that standing wave is the longest wavelength here, shown as n equals 1. If you put your finger halfway down the violin, creating a node here, and pluck, there you get 2 standing waves. And again, you can do that. You can keep adding nodes there and make different standing waves. But you can never have a non-whole number value. There can never be 2.5 standing waves on a string. So the circumference of a circular wave is a whole number multiple of the wavelength. Again, that's just another way of saying you can't have half wavelengths.
And if we talk about circumference, we can give that equation n times wavelength, where n equals the number of matter waves in a given energy level. So this was all just a theory that de Broglie came up with to explain quantum, the quantum behavior that Bohr's model gave. And it wasn't until a little while longer where somebody actually proved this theory. And how did they do that? They saw diffraction patterns of aluminum when you shined X-rays on the aluminum. So they shined electromagnetic radiation on the aluminum. That's shown here on the left side. And they got a diffraction pattern. And they got a similar pattern when they shined a beam of electrons on that aluminum. So that really showed that the electrons do possess a wave-like quality to them. Okay, so summarizing, we have the theory by de Broglie that all matter travels in waves. Energy of an atom is quantized due to wave motion of these electrons. And then the observation proved that theory. And if you remember, the previous theories put forth by Planck, Einstein, and Bohr were all to explain observations. This happened in the opposite direction, where the theory came first and the observation then proved that theory. And there was another theory put forth by Einstein and de Broglie. We're not going to really talk too much about it, but that was mass and energy are equivalent. Particles have a wavelength, and photons of light actually have a mass to them, have a momentum. And that observation was proven by Compton. So again, that was another example of where a theory came before the observation to prove it. And all this taken together was really the basis, where the culmination into what is known as quantum theory. Energy and matter are particulate, they're massive, and they're wavelength. So really what that means is energy and matter are all one and the same. So let's try a practice problem using de Broglie's equation. And de Broglie really came up with his equation to describe electrons, but let's do something a little bit different and try to describe a person in terms of their wavelength. So take a few minutes to answer this question based on a bicyclist and see what their wavelength is. Okay, the first step in this problem is we have to convert units. We can calculate a miles per hour and then convert that to meters per second. Or what I'll do is I'll just convert miles into meters and the total time into seconds. So we're given that the length of the race was 159.7 miles. And we want to convert that to meters. So if we do some dimensional analysis, we have that 1.609 kilometers equals 1 mile. And 1,000 meters are in 1 kilometer. If we do the math, that equals 256,957.3 meters. And I always keep all my significant figures until the end of a problem. If you wanted to, you could round that number too. You'd probably end up with something very close at the end. But I just as a form of habit, I keep all my significant figures until the end. The second step, we need to convert time into seconds. So the hours, we have 6 hours. So 6 hours, there's 60 minutes in 1 hour, 60 seconds in 1 minute. So minutes cancel, hours cancel. Our answer is going to be left in seconds. So 21,600 seconds. Then the minutes, there were 9 minutes. Nine times 60 seconds per minute equals 540 seconds. And finally, there was 1 second. So if we add all of these seconds together, 21,600 plus 540 plus 1, we get 22,141 seconds total in the race. So what does the average speed become? $256,957.3 meters divided by 22,141 seconds, which is 11.6 meters per second. Okay, now that we have his average speed, we can plug everything else into de Broglie's equation. So the wavelength equals h divided by mass times u, which u is velocity. So h is 6.626 times 10 to the minus 34. I'm going to write joule as kilogram meter squared per second squared, and the units are on Planck's constant or joules times second. And I'm just doing that to show you how the units will cancel. And it's also important to note that because the units are in joules, the mass has to be in kilograms that we use. And we're given the mass in the problem of the rider and the bicycle, so we need to add those together. So that mass total would be 80.8 kilograms. And then the average speed was 11.6 meters per second. So if we look at our units, we have 1 second cancel there. We have another second cancel there. One of the meters cancels. And the kilograms will cancel. So what we're left with is a wavelength in meters. And the number I get was 7.069 times 10 to the minus 37 meters. So you should get something around 7.07, 7.1 times 10 to the minus 37th meters. And hopefully you all got that answer. So de Broglie came up with this theory that everything has a wave property to it. So an electron acts as if it was a wave. And a man named Werner Heisenberg found that if this was really true, that would mean that it was impossible to really know the location and the velocity of a particle at the same time. This wave particle duality made it impossible to know both location and velocity. And this is what's known as Heisenberg's uncertainty principle. You can't determine the position and the momentum of an electron at the same time. And that's given by this expression, where delta x is the uncertainty in the position, m is the mass of the particle you're looking at, delta u, that's the uncertainty in the momentum or the speed, and this uncertainty has to be greater or equal to this expression, Planck's constant divided by 4 pi. And what this means is that because uncertainty has to always be greater or equal to this constant, what that means is if you know the position of your particle with greater and greater accuracy, you'll know the speed becomes less and less accurate, and vice versa. And Heisenberg was awarded the 1932 Nobel Prize for his work on the uncertainty principle. So let's try a practice problem applying this uncertainty principle of Heisenberg's. So again, we're going to use a cyclist as an example. So a cyclist with a total mass of 88.8 kilograms is riding at a speed of 12.68 meters per second. And we know that value, the speed, plus or minus 1%. What is the uncertainty in the cyclist's position, the delta x? All right. So the first thing we want to do here is calculate what the delta u is. So we're given it as a plus or minus 1%. So that's our uncertainty in the speed. So we're going to have to multiply our speed by 0.01 to find out what 1% is. 1% of 12.68 meters per second. And that is 0.1268 meters per second. So that's going to be our delta U. Okay, we're given the mass of the cyclist. H and pi are both constants. So if now we're ready to rearrange this expression to solve for delta x. So if we rearrange, we get delta x is greater or equal than h divided by 4 pi times m delta u. So that's 6.626 times 10 to the minus 34. Again, I'll write this out, expand the units, kilograms, meters squared, second. Four pi times 88.8 kilograms times 0.1268 meters per second. So one of the meters cancels, seconds cancel, kilograms cancel. our answer will be in meters. And what I get is delta x is greater or equal to 4.7 times 10 to the minus 36 meters. And you notice that that's a very, very small number. And that's why your book gives the example of that's how you can hit a baseball, because the uncertainty in the baseball speed and position is very low because it's so massive. But when we're talking about an electron, something with a very, very small mass, these uncertainties become much greater with compared to the size of the electron. And there's a good example in your book, an example problem they work through that shows you just how different these uncertainties are when you talk about something on the macroscopic scale like a cyclist and something on the microscopic scale like an electron. Sorry, forgot that I had a description of here of how to solve this, so I'll leave this here up so you can read that if you're interested. But again, the most important thing when you're doing an uncertainty question is that you need to find the delta x or the delta u value. And a lot of times you're not going to be given that value, but you're going to be given the uncertainty as a certain percent. So you have to remember you need to calculate the uncertainty and not just use 1% as the uncertainty. All right. Moving on to the final section of Chapter 7, 7.4, we're going to be talking about the quantum mechanical model of the atom. So this came about from Schrödinger. So in 1925, Schrödinger developed equations to describe the behavior of electron waves. And this really became the foundation of what's known as quantum mechanics. Everything before this was quantum theory, and Schrödinger took this a step further to make quantum mechanics. And he won the Nobel Prize, if you're interested, in 1933 for this work. And he made what's known as his wave equation, and that's this Greek letter psi. And this describes the motion of electron waves as they vary with location and time. Now, psi is sort of a meaningless number, or a meaningless value. What we're concerned more with is psi squared, and that's a probability function, and it defines what's known as an orbital, and that's a region of high probability of locating an electron. So mathematical solutions to these wave equations produce a unique combination of integers, and those are what's known as quantum numbers. Now, we're not going to really be concerned with what Schrödinger's equation is. I just want you to know what psi square represents. That's the probability of finding an electron. And also know that the solutions to Schrödinger's equation produce quantum numbers. There are three quantum numbers we're going to be concerned with in Chapter 7. The first is called the principal quantum number, or n, and it's also known as the shell quantum number. So it indicates the shell, which you can also think of as the size of an orbital or the energy of an orbital. And the rules for the principal quantum number are n has to be a whole number integer that's greater than 0. So it can be 1, 2, 3, and so on. The second quantum number is called the angular momentum quantum number, or L. And what L defines is the shape of an orbital, also known as the subshell. So really thinking about L, you can think about it as the shape. You'll see it sometimes mentioned subshell. I like to think of it as the type of orbital. Now the rules for L are L equals 0 to n minus 1 in whole number steps. So L is dependent on what n is. So if, let's say, n equals 1, L can only be 0 because 1 minus 1 would be 0. Now if n equals 2, L can be 0 or 1, and so forth. And the third quantum number is magnetic quantum number. That's m sub L. This defines the orbital's orientation around the nucleus. I like to think of it as simply defining the orbital itself. And the rules for m sub L are it can go from minus L to plus L, again in whole number steps. So if L is 1, m sub L can be minus 1, 0, and plus 1. Let's look at a chart. This is from a different text, but I really like this table. So if we look at the values of n, what values of L are allowed? So for n equals 1, we can only have one value of L that's 0. When L equals 0, we say that is an s orbital. We're going to be talking about these a little bit in a few minutes. When we have L equals 0, m sub L can only be 0, and there's only one orbital in that subshell. Now when n equals 2, L can be 0 or 1. Again, 0, L of quantum number L of 0 equals an s orbital, s subshell. When L is 1, that would be a p orbital. Now the values of m sub L, if L is 0, m sub L can only be 0, but if L is 1, m sub L can be minus 1, 0, or plus 1. Now, I really think you should try to remember this table. I think remembering this sort of a triangle is really helpful. I think that's much easier than try to memorize the numbers and the letters. If you can just remember this pattern of these triangles, I think that's really the easiest way to do it. And then know that m sub L, the values are the number of orbitals. So this first line, 0, there's only one orbital, and that would be an s orbital. Then the next step in the pyramid would be minus 1, 0, plus 1. Those are 3 orbitals, and p orbitals have 3 orbitals. And followed by this next step, you have 5 possible orbitals. Well, d orbitals have 5 orbitals, and we're going to look at these s, p, d, and f orbitals a little bit more closely. There's another chart that does sort of the same thing. You have the principal quantum number up here, 1, 2, 3, and then all the possible L, angular momentum quantum numbers, are shown. And this shows as splittings in a railroad track. You might like this. I like the other table more, but I'm including this just in case somebody likes this better. It might help you. So when we talk about the size and shape of an orbital, we use some terms. Radial distribution plot. This is a graphical representation of the probability of finding an electron in a spherical layer near the nucleus of an atom. So then what we have, we can look at different types of orbitals, and we mentioned these a little bit previously. An s orbital. You can think of an s orbital. S can stand for spherical. So there's a spherical shape of electron density that's highest near the nucleus. And the distribution exhibits a maxima at a finite distance from the nucleus. Now, what does that mean? Your book shows these sort of plots. You have a distance from a nucleus, and then the distribution of electrons, a plot. I find it easier to think about just as the spherical shape that would make. That would be just a sphere, a perfectly symmetric sphere around the nucleus. And that's an s orbital. So if we look at the s orbitals with different principal quantum numbers now, so if we have a 1s orbital, we see that the density is close to the nucleus. A 2s, the maximum density gets a little bit further from the nucleus. And 3s, the maximum density, again, is further still from the nucleus. What you'll also notice is that there's nodes. And these nodes, the number of nodes is equal to the principal quantum number minus 1. So there's one node in the 2s orbital, and there's two nodes in the 3s orbital. Let's talk about p orbitals now. Again, there's a radial probability distribution if you're interested in this, but it's more helpful to think of them in their three-dimensional shapes. And they look like sort of like dumbbells or bow tie, I guess. And they're three different p orbitals. The px orbital, it forms a dumbbell shape along the x-axis. The py, as you might guess, is along the y-axis, and the pz is along the z-axis. And if you add them all together, you get this sort of composite view. But it's much easier to think of them separately. And the nodes, again, are at the nucleus. So at the nucleus, there's a 0 probability of finding the electron. And now D is really the highest level orbital that I'm going to expect you to know how to draw. There are 5, the dxy. It's really just like adding two p orbitals together. You have 1 and 2. Sort of forms a clover. The dxy, the orbitals are occupying space between the xy axis, so they're in the xy plane. dxz orbitals are in the xz plane. dyz orbitals are in the yz plane. So those are fairly easy to remember. The next two are a little bit different. We have the dx squared minus y squared, and that is along the x and y axes. The orbitals are aligning with. And finally, the dz squared, where the orbital aligns with the z-axis. But this one also has this little circle shape around the center. So again, I would expect you to be able to draw one of these d orbitals and label it correctly, and be able to draw it along the correct orientation with the axes. So if you want to remember, I think dz squared is the easiest to remember, honestly, because it is just along the z-axis and it has a little hula hoop around the middle. But you should be able to draw these. Okay, let's try some quantum number practice. Write a set of quantum numbers that describes each of the three 2p orbitals. All right. So we have, sorry, these are horrible drawings. Okay, so we have three p orbitals, and the first quantum number is the principal quantum number n. So how can we find that? Well, we're given that in the problem. It says 2p, so that the 2 in front of the p indicates that the principal quantum number is 2. So n is 2. What's L? So we need to know L. What are the rules for L? Well, L can be 0 to n minus 1 in whole number steps. So if L is 0, that represents an s orbital. So we don't want 0, because that's for an s orbital, not a p orbital. So 2 minus 1 is 1. L equals 1 is representing a p orbital. So L is going to be 1 in our case for 2p orbital. And then next, the third quantum number is m sub L. So the rules for m sub L, it can be minus L to L in whole number steps. So L is 1. We can have a minus 1, 0, or a plus 1. So for each of these orbitals, if we want to write these out completely, we could have a n equals 2, L equals 1, m sub L equals minus 1, n equals 2, L equals 1, m sub L equals 0, and n2, L1, m sub L equals 1. So there would be the three sets of quantum numbers that would describe the three 2p orbitals. Okay, let's do another practice. How many orbitals can have a principal quantum number of 2 or a magnetic quantum number of minus 2? So if we think n equals 2, L can be 0 or 1.
m sub L. If L is 0, can be 0. M sub L, if L is 1, can be -1, 0, or 1. So what does that give us? That gives us a total 1, 2, 3, 4. So 4 total orbitals can have a principal quantum number of n equals 2. Magnetic quantum number m sub L equals -2. Well, if you remember, m sub L, it represents an actual orbital. So only one orbital can have a value of -2. So m sub L is the orbital. So only one orbital can have that value. Now I made orbitals here bold and italic because I wanted to bring up the fact that this question can also be asked a different way, and that is how many electrons can have a principal quantum number of 2 or a magnetic quantum number of -2. And then you would have to multiply your answers by 2. And we really aren't going to get into that today. That'll be next time. You'll see the reasoning behind that. I just wanted to point that out now because that sometimes students have a trouble with these questions because they don't read carefully enough if it's asking for the number of orbitals or the number of electrons. So just be aware of that. And I included this figure. This is something that I really like as a summary, where you have what was thought of as classic theory. Matter is composed of particles, and radiant energy has wave properties. And then there's the 3 observations. The black body radiation, photoelectric effect, line spectra that weren't really matching with classical theory. Planck came up with his theory about the black body radiation, and Einstein theory on photoelectric effect. This was that the theory was that energy was quantized. Bohr used the observation of line spectra and the theory of energy quantization to come up with a model for the hydrogen atom. And de Broglie used this model for the hydrogen atom to come up with his theory on matter waves. And Schrödinger and Born used that theory to expand into quantum mechanics. And that is quantum theory as a whole, that radiant energy and matter have both particle and wave properties. And in conclusion, we'll talk a little bit about what was actually on the title, the Schrödinger's cat experiment. And this experiment thought of by Schrödinger was he envisioned if you had, let's say, a cat in a box. And in this box, you have a radioactive sample. And this material has a 50-50 chance of triggering a Geiger counter. If you wait a certain time equal to the half-life of that radioactive material, there'll be a 50-50 chance that it'll give off radiation, trigger the Geiger counter. If that happens, you can hook the Geiger counter up to a hammer, shown here. That hammer, if the Geiger counter is triggered, will fall and break a vial of poison, let's say cyanide. And if that happens, the cat dies. So if that doesn't happen, if the radioactive material isn't triggered, it doesn't trigger the Geiger counter, the hammer doesn't fall, the cat's alive. So if you put all of this in an enclosed box and you don't look at it,
Um, the cat, because there's this 50-50 chance of triggering the Geiger counter, there's a 50-50 chance that the cat's alive and a 50-50 chance that it's dead. If you don't look in the box, quantum theory actually suggests that the cat is existing in both an alive and a dead state. It's really a superposition of the two. So it really gets very, very strange. When you take these theories that work on the microscopic level and you try to apply it to macroscopic systems, it's totally something that you don't come across in everyday life. But nonetheless, it's a very it's a theory that stood the test of time, and it really suggests that the universe is much more complex than we see on a daily basis. All right, so that's it for chapter 7. Next time we're going to be talking about chapter 8, which goes into the periodic table, the basis for the periodic table, and some periodic trends in the periodic table, and talk a little bit about chemical reactivity, atomic size, electron configurations. Those are important.